exact equations, 2.4, excuse me. We'll cover this and then I'll come back to 2.3. The end of 2.4 covers the introduction for integrating factors. Well, you need the integrating factor concept for 2.3. In the original book, this section comes before linear equations. Linear equations is 2.3, and then here in this book, 2.4 is exact equations. In the old book, exact equations comes first, and then after that we pick up linear equations. And the flow, I think, is a little bit better. So we'll cover that in this sense. Exact equations is the differential form that is tantamount to the vector form of a conservative vector field. So if you, for those who've had the Calculus 3 or physics, which physics is that? You all discuss the conservation of energy. Is it, okay, physics 2. So in physics 2, okay, so 1 and 2 physics. Definitely in Calculus 3. So whichever courses you've had, just one, you should be good. What we do here is we talk about the same thing, but just a different form of it. So we could talk about a potential function, which basically these f of x, y, or these functions of f, which is what they're set up to be. From there, you can form a vector field, and then you can show whether or not that vector field is said to be conservative or not. The process that you use for that is the same process for this, because for the exact equation, instead of talking about the vector field, we talk here about a differential expression. So it's the same concept, but I want to get and look at the derivative of that same function. I want to focus on the derivatives, because those derivatives, they give us smoothness, they give us concavity. That is the examination of the so-called vector field. Which directions are those vectors are going is based on the derivative. So here we consider the differential, and the question here is not whether or not the vector field is conservative, but whether or not the differential is exact. We're talking about the same thing. Okay. If you have a bucket that's half full, you can focus on talking about how half full the bucket is. Or you can talk about how half empty it is. Same thing, right? Just a different way of looking at it. That's the same thing with conservative vector field or an exact differential equation. Still talking about that same bucket, right? And it's half full, but it's also half empty. Same concept. So here we look at from the differential perspective, and the way it's presented is somewhat intriguing, because have you ever seen a duck swim on top of the water? You know, and it seems like the duck is not doing much. You know, it's just, But then if you look under the water, man, those flappers, they're just going. I mean, they're getting down, man. Well, that's what happens really with the exact equations, that the concept of it surface-wide is very simple. It's very easy to grasp. But behind it, there's some differentials that's actually doing the work. It's almost like the same concept with a person driving a car. Some people have no concept about what's going on with that engine, those pistons, and those gears. I mean, there's a lot of stuff going on, but I'm just so satisfied. I'm just driving my car, and it's a pretty car, but man, that car is just, it's spitting out oil, you know what I'm saying? It's taking in gas, it's blowing that gas up into fire, I mean, a lot of stuff is going on. Well, that's what happens here. Look at the definition. An exact equation is said to be a differential expression of m dx in dy is an exact differential in some region R. This is the same region R in Calculus 3 that we talk about, that surface region by which you want to build whatever type functions and different types of shapes from. some region R in the xy plane, if it corresponds, that's the kicker, if it corresponds to a differential of some function, f of xy. What is it? F of xy? That gets to that potential function over in physics. So some f of xy defined in R, a first order differential equation of the form m dx plus n dy equal to 0 is said to be an exact equation if the expression on the left-hand side is an exact differential. The differential is really the feet of the duck that's doing all the work. So here, we try to make it smooth by saying m dx plus n dy equal to 0. If this guy is exact, it really depends on if it corresponds to an exact differential. I'm going to show you one example to show you what I'm talking about. And then from there, I think once you see that, you appreciate the problems a little bit better. Okay. Look at the introduction. Although the simple first order equation, y dx plus x dy equal to 0, is separable, but this guy comes from an alternative form that says that the derivative of xy is equal to y dx plus x dy. This is said to be a differential form. Let me show you. I need to squeeze a page in there. Okay, good. Exact equations are based on exact differentials. A differential is of the form dx, dy, dt, dz, and so on. A total differential is written as dz is equal to the partial of f, partial derivative of f with respect to x at some point xy dx plus the partial of f with respect to y at some point xy dy. Or we can write it in short-term version. dz is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. Or if we have m dx plus n dy, then dz is said to be this partial of m with respect to x dx plus the partial of n with respect to y dy. This so-called total differential. Let me give an example. Let f of xy equal to x squared y. Okay, some in the third space, some paraboloid. If I take the partial derivative of f with respect to x, I get 2xy. That is, take the derivative. Here I focus only on x. I treat y as a constant or coefficient. Take the partial of f with respect to y. I take the derivative with respect to y. I treat now x as a constant or coefficient. So this is just x squared. So the total differential is dz is equal to, here, just going back to the form, the partial of f with respect to x dx plus the partial of f with respect to y dy. So the partial of f with respect to x is 2xy dx. Then plus the partial of f with respect to y, this is x squared dy. So that's like the groundwork up under the water that's going on. Now in this class, all we consider, we say here, consider the differential equation of the form 2xy dx plus x squared dy equal to 0. Then they say solve that. So there's some stuff that was going on before that. So in the book, they have like number 1, it'll look like this guy right here. Number 2, it'll look something like this. But there was some work going on behind that to even get you to this form. So what's the total differential? What is that all about? Basically, all that is, do you recall in Calculus 1 when you had 2 terms multiplied and they asked you to take the derivative of that? You use the product rule. And then when you use the product rule, you have to use a chain rule. So if you take the derivative of x, then it's times dx, whatever. Take the derivative with respect to y, then times dy. Well, that's the same thing. It's a total differential. That's all that's going on. So you got some product that they've already found the derivative and expanded it. And so now basically to solve the differential equation, you want to use some type of integral, some antiderivative to get back to the original function you're solving for, little f of xy. Now the question is, you can get back to little f of xy if the differential is in this form. And so we say that it's exact. That is, it exactly matches up. The differential equation exactly matches up to some type of total differential somewhere. It's exactly the same. If it is, I can solve it very easily. Now, I'll show you the very simple method of solving this. So let's get back. So here, the definition for an exact equation. You got some form of m dx and dy. We said that this is an exact differential. Here, we call the m dx plus n dy equal to 0 a first-order differential equation. It's an equation because it's an equal sign that's set to equal to something. It doesn't have to be 0. It could be a number over there or some other term. That doesn't matter. This matches up indeed to an exact differential, a total differential. The criteria for so-called exactness here, that when you consider m is the coefficient of dx, and you consider the coefficient for dy, we call that n. If the relationship, that is the partial derivative of m with respect to y, is equal to the partial derivative of n with respect to x, then we say that we have the criteria for an exact differential. Why is that the case? You recall, to even build the so-called exact equation, it came off of that so-called total derivative or that product using the derivative. You take a product, take the derivative of it, you expand it out. So we're saying that if you have that, if I go back to really find out what's going on, that if the partial of m with respect to y is equal to the partial of n with respect to x, then we say that the differential equation is exact. If it's exact, then we have a simple method to solve it. Okay? If it's exact. So how do you know if it's exact? We just check this criteria. And we can do this for the 2 space with some rectangular region in the xy plane. Here that these functions m and n are said to exist on, then a necessary and sufficient condition that this differential expression to be exact, that you must have this. Now, in higher levels of differential equation, the statement necessary and the statement sufficient they're very strong clauses, and there's a lot. Again, it's that duck that's swimming. There's a lot going on underwater. We see a statement, but it means a whole lot in the study of differential equation. So if I have this, then I can easily get to the answer. Now, what I did here for you was to put in here, I think, a very simple, straightforward method to solving a differential equation. How to solve an exact differential equation. First, you check the criterion. Is the partial of m with respect to y, is that equal to the partial of n with respect to x? If that's the case, then use the following method. Integrate each differential coefficient with respect to dx and dy. So if there's a dx there, you integrate with respect to x. If there's a dy there, you integrate with respect to y. If it's exact, you're going to have some repeating terms. So you're going to delete, if you got one term, then you have a copy of it, then you delete that extra. So delete keeping only one of the unique terms. Keep all other terms that are different, and then adding a constant yields the solution to the differential equation. And this remark here deals with some problems toward the end of the section, I think numbers 31 to 37 or something like that, where sometimes the above method does not yield an exact form. So you can force the DE to be exact by using the following method. And won't get to that today. Let's look at some problems. So here, this is saved toward the end. Again, this gets into what we call an integrating factor, which becomes the introduction then for section 2.3. So let's see here. We solve this. So m is equal to 2x minus 1, and n is equal to 3y plus 7. Now, remember, the form has to be m dx plus n dy equal to 0. The m is associated with dx, and the n is associated with the dy. So I'll take the partial derivative of m with respect to y. Well, here, there's no y forms here, so the partial derivative, or the derivative with respect to y, is 0. The partial of n with respect to x, well, there's no x there, so it's like taking the derivative of a constant. I get 0. So the criterion says that as long as the partial of m with respect to y is the same as the partial of n with respect to x, we say that it's exact. If it's exact, then we use our method. Our method says integrate. This is 2x minus 1. Here I'm going to integrate with respect to dx, plus integrate here with respect to dy. Integral of 0 dx. So here I integrate there. I get x squared minus x plus 3y squared over 2 plus 7y is equal to c. There's nothing repeating. Let's see if I can. x squared minus x plus 3y squared over 2 plus 7y equal to C. There's no repeat. That's the answer. Is that okay, Trey? Okay. All right. If it's exact, I integrate with respect to dx, integrate with respect to dy. If there's any repeat, you get rid of one of them, you keep one. Yes, sir? Let's see. All right. So remember the form. The form of the problem is this, right? M something times dx plus something else times dy equal to 0. So I want to take m, take its partial with respect to y. Is that the same as the partial of n with respect to x? That's the criterion, right? If that's the case, if it's exact, then we integrate with respect to the differential. Dx is a differential. Dy is a differential. All right. Let's look at the next one. All right. So here, m is equal to 5x plus 4y, and n is equal to 4x minus 8y to the third. I take the partial of m with respect to y. That's equal to 4. Then I take the partial of n. See, the partial of m with respect to y. What here, if I'm taking the derivative with respect to y, anything else is treated as a constant or a coefficient. So here, taking 5x is looked upon as a constant with respect to y. So the derivative of a constant is 0. Then the derivative of 4y with respect to y is just 4. The partial of n with respect to x, there's a 4x, that derivative is 4. Here, y is treated as a constant with respect to x. So here they're the same. So we say exact. So I go back to the original form, take the integral with respect here to dx plus the integral of 4x minus 8 y to the third dy is equal to some integral of 0 dx. Integrate with respect to x here, so this is 5x squared over 2 plus 4xy plus integrate with respect to y on this side, so this becomes 4xy minus 8y to the fourth divided by 4. That's 8 divided by 4 is 2y to the fourth. That's equal to C. Do I have some repetition? I'm at 4xy. So I'm going to delete one, keep the other. So here we have 5x squared over 2 plus 4xy minus 2y to the fourth is equal to C. You can leave it like that, or if you don't want to have a fraction, I think the back of the book has this answer, 5x squared plus 8xy minus 4y to the 4 is equal to C. Okay. Either way is fine. So the next one, this is m dx plus n dy. So m is equal to sine y minus y sine x. N is cosine x plus x cosine y minus y. Take the partial of m with respect to y. So this is the derivative, not the integral. So here I get cosine y minus, take the derivative of this y, that's just minus 1 times its coefficient, sine x. Again, I'm taking the derivative with respect to y. Right? Take the derivative here of the partial of n with respect to x. So this becomes negative sine x, plus take the derivative of this x, that's 1 times its coefficient, cosine y. We'll see if that matches up. Cosine y, positive cosine y there, negative sine x, it's exact. So if that's the case, integrate this m dx with respect to dx. Plus integrate this other side with respect to y. Integrate that 0 over there. We got a constant. Just go ahead and put that there. First, integrate with respect to x. So this becomes x sine y plus y cosine x. The integral of sine x dx is negative cosine x. Right? So negative times that negative gives us a positive there. Then plus integrate with respect to y. So this is just a constant term. So this is a y times that cosine x. Integrate this cosine y with respect to y. This is plus x sine y minus y squared over 2 is equal to c. Now I have an x sine y here and an x sine y there. So I'm going to get rid of one of them. And then I have a y cosine x and a y cosine x there. I get rid of one of those. What I have left is my answer. This is x sine y plus y cosine x minus y squared over 2 is equal to c. Yes, sir. Again, it's that duct that you don't see those legs moving. Right? What's happening is this integration is over a form, and you're actually overlapping one surface area with another surface area. So the overlap is what you're taking out of. Yes, sir. It's like the union of two sets, but part of the union, because of the exactness, part of it overlaps with the other union set, so you subtract that duplication. That's actually what's going on. That's what's under the undercurrent. You know, the explanation of that is a theorem that my professor had proved when he was in school. This is actually called the Stallworth method, named after one of my deceased professors. Yes, sir. Somebody had the hand up? Yes. Okay. All right. See if I have time for maybe a couple of more, and then as my elementary school friend named Trey used to say, not this Trey, but my friend Trey would say after we would be outside playing, he said, look, I'm going to tell you one more thing, I'm going to let you go. You know, as if, you know, I always thought, he's not holding on to me, you know. I'm going to let you go when I tell you this. So when I get through working this problem, maybe another one, I'll let you go. So now watch this guy. This is not written in the form. This is not in the form of m dx plus n dy equal to 0. So we have to write it in that form. That means that I have to multiply through by the dx. So I get this 2y minus 1 over x plus cosine 3x. This is times dy plus parentheses y over x squared minus 4x to the third plus 3y sine 3x. That's times dx is equal to 0. Now, if you're not careful, you'll get mixed up. So I'm going to write it one more way so that it can actually be in this form. Because notice that the dy is first, and then the dx, but it's supposed to be m dx plus n dy. So I don't get confused. And you'll start taking the partial derivative of the wrong thing just because you see this guy written first. But this is not m. This is n. Right? It's n times dy. Right? I mean, if you know that, you can just say that, but for me, I'm going to write it to make sure that it matches up to the form. So m is this expression here. Well, since that's pretty long, let's go ahead and just take its derivative, the partial of m with respect to y. This is 1 over x squared. X squared. And then here the derivative of a constant is 0. Then this is plus the derivative of this y, which is just 1 times its coefficient, 3 times sine of 3x. So now, what about n? N is that 2y minus 1 over x plus cosine 3x. So the partial of n with respect to x. So here we take the partial, take the derivative of 2y with respect to x, that's just 0. And then take the derivative of this 1 over x. So that's the, but negative x to the negative. Need to put a parentheses in there. So this is just x to the negative 2. So here, this is 1 over x squared. Take the derivative of this term with respect to x. So this is minus 3 times sine of 3x. They're almost, but look, this is a plus, and that's a negative. So they're not exact. Yes, sir. Here, this is the derivative of m with respect to y. So I'm only taking the derivative with respect to y. So what's the derivative of y here? Just 1 times its coefficient, 3 sine 3x, right? It's the partial derivative. So it's not the total derivative, just the partial, which means if it's the partial with respect to y, only take the derivative with respect to y. Treat x as a constant or coefficient. Okay? Yes, sir. Okay. All right. See, I guess we got time for one more. Let's see, that's number 9, and that number there, 15 looks good. What else do we have here? And they look good as well. They all look good. They all look good. Okay. So let's see, where are we? All right, let's look at number 9. So is this problem in the correct form? No? So what must we do to write it in that form? That's right. So we have to get that right side over to the left side, get everything on the same side. Very good. So this is x minus y cubed plus y squared sine x dx this is minus now, parentheses. Yeah, in my head I know, but yes. But for you, and I'll show you when I work it out, it's a negative applied to each of those terms, right? So we clearly see that this is m. Right? And this is n. So I take the partial of m with respect to y. So here, this derivative of x with respect to y is just 0. This becomes negative 3y squared. And then the derivative of y squared is plus 2y times its coefficient sine x. On the partial of n with respect to x, remember there's a negative attributed to each of those terms there. So we take that into consideration. We take the derivative. So it's the derivative of minus 3x y squared with respect to x. It's just negative 3 y squared. Then the derivative of this is a negative 2y cosine x with respect to x. This becomes a negative sine x. Negative times that negative is positive. Right? Negative times the negative from the derivative of the cosine becomes positive 2y sine x. So they are exact. They put that there to throw you off because it came out initially, it was something equal to something else. Right? So if you looked at that and checked the exactness, they wouldn't be exact. They would differ by a negative sign. And you would say, okay, they're not exact, I'll move on. But they are exact. So since they are exact, we're going to integrate here with respect to the differential. We're looking at this guy right here. So this is x minus y cubed. Let me finish this one, then we'll go plus y squared sine x dx minus the integral of 3x y squared plus 2y cosine x dy, and gives us a c over there. So quickly we integrate. We're here with respect to x, so this is x squared over 2 minus x y cubed, right? Minus y squared cosine x. Right? What's the integral? Here I'm integrating. What's the integral of sine x? It's negative cosine x. This is minus, integrate with respect to y over here. So this is 3x y to the third divided by 3. Don't forget that negative sitting out there as well. Then we integrate this 2y cosine x with respect to y. That becomes 2y to the second divided by 2, minus signs. This is minus y squared cosine x. That's equal to c. We look at the repeat. Let's see here, x, negative x y to the third. That's the same thing as here. So I get rid of that guy. So it's the same. And then what about this negative y squared cosine x? Negative y squared cosine x. I get rid of one of those guys. I tell you, you know things are not right when you write with something and nothing comes out. I'm telling you, man, just give me that old-fashioned chalk, man. It just makes life a whole lot better. Okay. As our mechanic friend in Orville, Alabama, Tidbit, always says, okay. So this is x squared minus 2x y to the third minus 2y squared cosine x is equal to c. Just multiply everything by that 2 right there. Okay? Yes, sir. What was that again now? Right here. You could say plus and put the negative there and put the negative there. Is that what you're saying? Yeah, that'll be fine. Yeah, that might be easier, Yes, sir. Thank you.